A function f of xy on r square has the following partial derivative, this and this. Then f has directional derivative in all direction everywhere. F has a derivative at all points. F has directional derivative only along the direction 1 1 everywhere. F does not have directional derivative in direction everywhere. Now first understand what is the meaning of each given option. If you focus on option A, f has directional derivative in all direction everywhere, it means suppose this is a domain point. Suppose this is domain and we are finding directional derivative at this point as big O. Suppose all directional derivative in all direction everywhere, it means if you are extending this as a vector at possible length, it means everywhere. If you fix this length, then you are saying directional derivative is existing in the direction of certain vector at some magnitude, means length of the vector. This is the meaning directional derivative, directional derivative and everywhere. Now option B, f has derivative at all points. So option A and B are quite similar but have little bit difference. Now understand what is the difference. Suppose this is domain and you are finding directional derivative at this point. Suppose all directional derivative is existing at this point. It doesn't mean function is continuous at that point. If directional derivative is existing at a point, all directional derivative everywhere at a point, it doesn't mean function is not function may be continuous or may not be continuous at that particular point. And you will come across many situation or problems where all directional derivative existing but function is not continuous. Now if function is derivative at point, it means function is continuous at that point, but directional derivative not imply the continuity at that point. So this is the little bit difference in option A and B, but they are here quite similar. So find directional derivative, it means suppose this is a vector v in which we are going to find directional derivative, and this vector v is any direction derivative. So let's consider v as v1 v2, or you can take vector u as u1 u2. Suppose you are going to find directional derivative at a point u, sorry, in the direction u at the point v. This is meaning in direction and at a point. And these two are random points. These u and v are random points of r square. So if this directional derivative is existing there at u, then we will say all directional derivative existing in all direction and everywhere. In all direction and everywhere, it is important. Function partial derivative is given to us, it means this is some compute made easy computation of directional derivative because partial derivative is known to us. So find directional derivative of function means need to find gradient f, and this is gradient f we know as fx is x square and fy is y square. So this one will be x square I hat plus y square j hat, and suppose vector u is by the constituent u1 u2. So take dot product with this vector. I'm not saying vector u is unit or not. U may be unit or not. Some examiner or research scholar or many persons take unit vector when they find directional derivative, but it is not permanent concept to find directional derivative in only and only unit vector direction. It may be anyone, but if you are taking unit vector, the concept or motive of taking unit vector is that you are finding directional derivative at unit length or at unit length or unit modulus. Now this is by, now x replaced by u1 and y by u2. So u1 square plus u2 square, because when we take a dot product, I and j remove when we take dot product of two vector quantities. This means u1 square plus u2 square. If we are taking at a point, at a certain point, u1 and this is also x square, y square will be there. Some little mistake here. I'm going to take dot product of gradient f with vector u. So it will be x square u1 plus y square u2. This is perfect here. Now put the value of the point A or point V as V taken, and V is V1, V2. So replace x by V1 and y by V2. So it will be V1 square u1 plus V2 square u2, and this value is existing everywhere. Whatever the value of u and v, means directional derivative is existing whatever value we choose, or random points of r square, means all directional derivative existing. Also you can check function is differentiable everywhere, there is no condition. So option A and B are both true.